This is me. Nearly 7 years ago, a 10-year-old introvert just beginning her journey through first LEGO League robotics. Little did she know that the very hastily put together LEGO robot that she held in her hands that day was going to be the catalyst to propel her into a whirlwind of opportunity and possibility in science and engineering. But before we get into that, I think some proper introductions are in order. Hi everyone, I'm Audrey. I'm a junior at Eastlake High School in Sammamish, Washington. I'm a big tree hugger, a Shakespeare enthusiast, and a poetry nerd. But the most important thing about me, I love robots. So much so that I tend to spend half my free time competing with, mentoring, and volunteering for 3 different FIRST robotics teams, and the other half of my free time building robots and other assorted contraptions on my own. It's quite nerdy, actually. But even though building robots is one of the most geeky things I could be doing with my time, it has not only led me to discover my passion for creating things to better our world, but it has also led me to believe that what we perceive at first glance to be impossible, when approached with a creative eye and tenacity, can be redefined, overcome, and innovated. Most of the time, these innovations are uncovered at the intersection between many scientific fields and concepts. And today, I hope to take you all on a journey through one of my most recent projects, tackling a problem yet to be solved by modern researchers, with nothing but a love for robots. Before diving into specifics, I want you all to imagine that you had to choose between losing your sight or losing your phone. Most likely your answer is your phone, but what if you had to choose between losing your sense of smell or your phone? I'm guessing quite a few of you would rather get rid of your sense of smell. Why is that? Smelling might not be as important as your phone to your daily activity. It's probably not as important as your sight or your ability to hear things around you. Sometimes I wish I didn't have a sense of smell, like when I'm sitting next to my dog. But what if you could smell when food is going bad? What if you could smell dangerous chemicals before they contaminate a building? Over the past few decades, we've been able to mimic human senses using technology. For example, probably everyone here has used a camera, a sound recorder, or even a touch sensor. But how many of you have used a smell sensor? I'm guessing very few, if any. Detecting a smell using an electronic nose, or an e-nose, is still a very new concept in modern research, and I was immediately fascinated by the implications of this technology. Smell sensors could be used to determine when a food has gone bad, or even identify the source of a hazardous gas leak. Immediately, I became really interested in how these e-noses work, and I wanted to see if it was possible to create a device to determine where this dangerous substance was coming from. So I turned to what I was most familiar with and began engineering a proof-of-concept odor-localizing robot to determine the source of an airborne odor. And this brought about the creation of Alvin, the autonomous localization vehicle with an intelligent nose. Think of him as a robotic dog that can find the source of a gas leak using his nose. Now, Alvin was not thrown together and working in a matter of days, rather engineered over the span of a few months. So once I decided I was going to tackle this large project, how did I know what to do first? Well, I reasoned, a good place to start seemed to be by looking into how the structure and characteristics of animal noses allow them to smell. So I first looked into features of noses that were particularly keen, namely those of dogs. And what I found interesting was that dogs breathe in and out 3 to 5 times very, very fast whenever they catch a scent. This is because they stir the odor molecules in the surrounding air to gain a better reading of what they smell, essentially. As most other species, dogs also have 2 nostrils that sniff in stereo, allowing them to have a 3D sense of smell. Naturally, the first step in designing Alvin was creating this e-nose, or an artificial olfactory system that modeled a real dog nose in terms of function. I looked at what I had at my disposal. No real olfactory receptors, no high-tech lab with a mass spectrometer, rather an Arduino and a computer. In a series of models and subsequent 3D printed prototypes, a bio-inspired e-nose slowly took shape with the help of CAD, or computer-aided design, and a rubber pump, with the goal of sucking contaminated air into a secure chamber for odor identification. This e-nose was designed to act like a syringe. When squeezed, air would be pushed out of the pump. When released, air would fill the chamber. But I didn't just build one of these, I built 2, mimicking our 2 nostrils. As a result, this robot would be able to differentiate between odor concentrations in either nostril. In order to actually detect odors in the air, though, each nostril I then equipped with a small Arduino sensor, at the time capable of detecting rubbing alcohol. That way, whenever the e-nose was engaged and air was drawn in through the system, the sensors inside the nose would obtain readings of whatever odor was present in the surrounding air. Now that I had a robot, the next step was to program it and make it move autonomously or on its own without a human having to intervene to find the source of an odor. And after reading a few research papers on attempts to do exactly this, I realized that it was no easy task, even for professional researchers. Odors, unlike light or sound, do not travel in waves, rather in unpredictable plumes. Think of plumes as floating masses, like clouds, that when released from a source travel in all directions. This has made detecting odor sources fully autonomously almost impossible by a robot. And then I came across something rather interesting. As it turns out, moths and lobsters navigate through odor plumes to find mates and food using their antennae. Essentially, in a cone-shaped odor plume, a moth or a lobster will zigzag in and out of the cone's perimeter, eventually closing in on the odor source. Now this was cool. So I sat on my couch with a piece of graph paper and a pencil and tried to come up with something, anything really, that would allow me to teach my robot how to find an odor source, just as those moths and those lobsters had. Soon, however, my mind started drifting off to the pre-calculus homework I still had to do. We were working with the unit circle, so daydreaming about trigonometry, I drew a coordinate plane on my paper. And then it hit me. I could use a coordinate plane and some math to make my robot decide in which direction to turn and by how much, based on its sensor readings. And this turned into the algorithm used by Alvin. Finally, a use for math class. In a nutshell, this unique algorithm uses the difference between the sensor values coming from both the right and the left robot nostrils and the maximum value between them to determine in which direction to turn and at what angle to turn in order to find an odor source. Every time Alvin sniffed or inhaled air, the left and the right readings would go through this algorithm to move one step closer to where the odor was coming from. So I wrote all of this into code with the help of some crash courses and an Arduino handbook and uploaded it onto my robot. I was finally ready for my first round of testing. Unfortunately, but expectantly, I encountered my first major issue here. Even though both robot nostrils were being exposed to the same amount of the odor, they were showing vastly different readings. We're talking about 300 versus 1,000 units. How many of you have programmed an EV3 or a robot with sensors and it caused you some trouble? It's possible that this was because your sensors were not calibrated, and it turns out this was the issue with mine. However, unlike EV3 sensors, even with the suggested calibration program, I was unable to fully calibrate my Arduino sensors. At this point I thought that was it. How was I supposed to use uncalibrated sensors or calibrate them myself? It was almost impossible. Almost. And that's when I decided to do something creative about this issue. I needed to create a near airtight environment for the sensors, so I took a glass jar from my garage and stuck two MQ sensors facing each other inside, placing a piece of paper towel at the bottom of the jar. The top was covered with plastic wrap, and every 60 seconds I squeezed a constant amount of rubbing alcohol into the jar so that it landed on the paper towel below. And I recorded these sensor readings and concentration at 30-second intervals. And then I graphed each sensor using a simple Excel spreadsheet. Using the Excel graphs, I then found trend lines that fit my data points and did some math to determine the inverses of each of those trend lines. This effectively allowed me to normalize or calibrate my sensors with a little bit of innovation and math. So I thought, well, this is great. Calibration worked, so the robot's going to work, right? Wrong. When I sprayed rubbing alcohol at the robot during testing, its nose was not able to detect any change in alcohol concentration in the air, no matter how much alcohol I sprayed or how close I was to the robot. It appeared as though rubbing alcohol was too dense to stay airborne long enough to be detected by the robot. And even though I could have given up and concluded that it was impossible to detect a substance using my prototype robot, I decided to try using another pair of sensors and detect a different substance instead. But what other gassy substance can I use? I mean, I can have my dog eat some beans, or I can use butane, which I have plenty of in the form of a gas lighter. I used the same sensors in a jar method of calibration for this new set of sensors, and once again used some math to normalize the sensor readings. I swapped out the old alcohol sensors in the robot for the new butane ones, and upon testing these newly calibrated sensors on the robot, realized that density had been my problem, and Alvin was able to actually detect butane concentrations from various angles and distances. After tweaking and modifying the robot code for some time, Alvin reached the point where he was able to determine in which direction to travel and by how much based on these now calibrated sensor readings. So as far as my engineering goal in designing a proof-of-concept odor localizing robot, Alvin's implementation was a success. And here's a quick glimpse of what Alvin was finally able to do. However, while I concluded success, there were some major restrictions and barriers in this project. For one, Arduino MQ sensors are by no means the most reliable nor accurate, and they can become saturated very easily. This was one of the biggest issues that Alvin faced in testing, as the sensors were unable to fully desaturate or get rid of what they were smelling before the next sniff. But perhaps the biggest limitation of this project was testing. Unfortunately, due to safety and space constraints, it's not possible at this time to simulate an odor plume strong enough for Alvin to locate the source of in my current workspace in a safe manner. And it's possible that it's because of these large challenges that odor tracking research is so limited. Current research is looking into semi-autonomous odor localization because of the difficulty and near impossibility of fully automating robots to carry out this task. As far as my project though, with enough tweaking, modifications, and robust field tests, Alvin could pave the way for efforts in autonomous gas leak detection and even natural disaster recovery. Alvin was a multi-month project that began back in 2019, and since I have had the incredible opportunity to share him at the virtual Central Sound Regional and Washington State Science and Engineering Fairs, as well as the Regeneron International Science and Engineering Fair, or ISEF. More recently, I was able to share my work with a researcher who actually wrote a paper that I frequently revisited during my work. If doing independent research as a high schooler has taught me nothing else, it has taught me the importance of not only exploring and asking questions, but sharing what you found, whether that be by entering competitions, writing a paper for publication, or attending a conference like TEDx. Scientific discovery is a lot more useful when it's shared, but that is by no means the only thing that doing research has taught me. It has taught me how to meticulously document my work, keeping a logbook, annotating research papers, commenting my code and CAD models. It has taught me how to be creative in the face of challenges. I work almost exclusively out of my garage, and it has almost forced me to be creative with the resources I have, hence the sensors in a jar calibration. It has taught me the importance of sharing research, but also receiving feedback for your work, even if that feedback may not be the nicest. But most importantly, it has taught me that product is unimportant without process. In other words, it doesn't matter if you've designed new odor tracking technology or an improved jet engine. What matters is how you got there and how you overcame obstacles, how you redefine the impossible with your wit and innovation. I started this talk today by sharing this picture of me as a 10-year-old. That girl had no idea that in 6 years, what began as an after-school hobby would eventually lead her to design improved saltwater batteries, engineer a novel method of microplastic detection, or attempt to build an odor-localizing olfactory system. Quite frankly, she didn't even know what those things were. But by drawing previous knowledge from STEM fields she was already comfortable with, such as robotics and 3D modeling, and investigating entirely new concepts such as odor propagation, one girl's crazy idea of attempting to build a robot that can find a gas leak using nothing but its nose became a reality. If you take nothing else from my talk today, I want you to remember this. You don't have to be an adult to do relevant and groundbreaking research. You don't have to work in a lab with super fancy equipment. All you need is a little bit of inspiration, a willingness to take risks, and a whole lot of out-of-the-box creativity. In redefining the impossible, we must start by attempting the impossible. Don't be afraid to ask questions. Don't be afraid to seek answers. Don't be afraid to attempt to change the world now, as a kid, as a teen, as a young person. You never know where it might lead you. And that little girl certainly didn't. Thank you.